Hey everybody, it's my great pleasure to introduce the speaker this week today. So Professor Hyungrok and is a professor of mechanical engineering at Seoul National University. Before he joined Seoul National University in 2015, he was an assistant professor of aerospace and mechanical engineering at the University of Notre Dame in the United States. He earned both his PhD and master degrees from Stanford University in 2009 and 2006, respectively, and his bachelor degree in 2012 from Seoul National University. Now he's back to Seoul National University as a professor there. His current research activities are mostly focused on the development of hypersonic propulsion systems, including hypersonic vehicle design, high-speed combustion stabilization, and laser diagnostics in high-speed compressible flows. He has received the 2019 Global Power and Propulsion Society Early Career Award and the Air Force Young Investigator Program Award in 2015. So in the following about 45 minutes, and Professor Do will talk about high-speed combustion for hypersonic flights.
Okay.
So Hyungrok.
Thank you for the introduction. Yeah, thank you for the introduction. So it's my great honor to present my work here. And today I'm talking about the high-speed combustion for hypersonic flights. And today I'm mostly focused on the application aspect of the combustion science. So there are lots of relevant technical issues for enabling the hypersonic flights. So today I'm listing just a few interesting problems you might be interested in. So far, I don't have the quite right answers yet, but there are many interesting questions and problems you might be interested in. So let me start with some introductions for hypersonic flights. So basically there are three ways of flying the vehicles at hypersonic speeds. The first one is probably by the ballistic missiles. So the rockets are powering these ballistic missiles. So you can go up to like a few thousand kilometers, and it is accelerated at very low gas density regions. So the drag force you need to worry about is pretty low. So you can easily reach to Mach 20 or 30, but it is far away from the surface. So re-entry is another significant problem you need to consider for these hypersonic flights. And there are other ways of hypersonic flight in atmosphere. So hypersonic glider is utilizing aerodynamic forces in the atmosphere. Because this guy is using the aerodynamic force, you should fly in the atmosphere that is generating aerodynamic forces to make the hypersonic flight enabled. And this power, this vehicle is powered by rocket engine as well. And another one, the last one, is the scramjet powered or air breathing powered propulsion systems, which can fly at relatively lower altitude below 50 kilometers. And this guy is taking air from the atmosphere for generating thrust. So you should fly at relatively low altitude, typically between 20 kilometers up to 45 kilometers. And this guy is taking air from the atmosphere, therefore the influence of the atmosphere is quite severe. So you need to consider the interaction between the combustion reaction and the ambient air is quite critical in this case. So today I'm talking about some a few issues with the rocket engines and scramjets mostly. And I will be happy to get any comments or questions for this recent research. Okay, so for rockets, we need high-speed and high-pressure combustion reactions stabilized in a main combustor. And for air-breathing scramjet engines, you need to stabilize the combustion reaction in supersonic flow. And you also need to consider the interactions with the environment, turbulence and velocity and the compression ratio. And these are all directly affecting your combustion behaviors. Okay. So this picture is a very famous one. I would say this is SPACEX developed RAPTOR engines, and 29 RAPTOR engines are assembled for generating the thrust, which is double the thrust of Saturn V rockets, which launched NASA astronauts to the moon. So this powerful engine looks like this. So it is driven by two high-end, high-performance turbopumps, which is for methane fuel, liquid methane fuel, and the other one is for liquid oxygen. So the methane will be compressed by this turbine pump, and the pressure can reach 640 bar. This is extremely high pressure. And this high pressure and low temperature fuel is circulating around the combustor and the nozzle so that the fuel can be heated up and this high temperature part can be cooled down. And the heated liquid methane is getting into the pre-burner, and it is mixed with a small amount of oxygen to be burned partly. So the methane-rich gas will be generated, and it is driving this turbo pump, and the pressure will be decreased down to 321 bar. And this high pressure methane and oxygen will be injected into the main combustor, and it's burning at about 300 bars. And 300 bar is higher than the critical pressure of the carbon dioxide and water. So the combustion product gas will become a supercritical fluid in this region. So understanding the supercritical flow behavior is quite important with this kind of engines. Okay, so for maximizing this gigantic engine, I mean, the size of the engine is not gigantic, but the power generated by this engine is gigantic, I would say. So the fast combustion flow should be stabilized, and the combustion reaction should be stabilized inside, and the combustion instability should be considered inside this engine. Okay, so here is a very simple and well-known example of the gas turbine combustor. So before the air is getting into the combustor, you have a swirler, and this swirler is generating a very strong swirling flow in the combustor, and which is generating recirculating flow. So the high temperature combustion product is coming back to heat up the fresh fuel and air mixture. So the flame can be stabilized, and the intense combustion reaction is now stabilized in a relatively narrow region here. However, if you increase the fuel concentration and flame propagation speed is relatively slow compared to the flow speed, then you see the destruction of this stabilized flame structure. So you don't have any recirculation region or source in the combustor. So your flame is long stretched and the combustion region is extended, and your combustion efficiency will drop. So we don't want this situation. We want to keep the combustion reaction in a designated area, and we want to maximize the combustion efficiency. So source and recirculation regions will be used for the same purposes. I'm talking about the methane fuel. So previously, hydrogen fuel has been used for rocket propulsion, but hydrogen is difficult to compress and liquefy. And methane has some benefits over the hydrogen fuel. So that's why methane has been used for recent high pressure and high performance rocket engines. Okay, so we want to stabilize the flame in a broad range of pressure ranges from 1 bar and above 200 bars. So we developed some active combustion stabilization technique, which is the injection of cross jets. So these jets are, in fact, the subsidiary oxidizer. So fuel-rich mixture is injected here, and you have 3 streams on the side to generate extra recirculation zone behind. So maybe you can expect that the flow conditions and the pressure conditions and temperature conditions vary while you're pressurizing this combustor from 1 bar to 200 bar. So for stabilizing the flame with the varying flow conditions, you need some active flame stabilization techniques. So this is the basic structure of these combustors, and you have a pilot burner here, and you have the main injector, and you have some holes, and these holes are injecting the subsidiary oxidizers, which is generating recirculation region behind. Okay, so we could successfully stabilize the flame from low pressure to very high pressure conditions. And for this testing, we have collaborated with Dr. Daegun Lee at Korea Institute of Energy Research. And the research has been supported by Korea Electric Power Corporation. So on the left-hand side, you see the flame structure in subcritical condition. The pressure is between 20 to 50 bar. So you see a very unstable flame here, very near the root of the flame. So this is happening while you're increasing the pressure and change the flow rates. So for stabilizing this kind of flame, while you're raising the pressure, you need the extra recirculation zone. This has been generated by the subsidiary oxidizer injection. And in the supercritical condition, you see a quite different structure of the flame. And in fact, it is quite difficult to see. And under this supercritical condition where the pressure is above 100 bar, oh, I forgot to mention that the oxidizer consists of CO2 and oxygen, and 30% oxygen and 70% CO2 to keep the temperature not too high in this case. So most of the combustion product gas and the diluent gas are in supercritical condition. So in the supercritical condition, you expect that the density of the fluid is very high and it behaves something like some liquid and gas. So you see some significant distortion of the refractive index field here. So optical measurement becomes quite difficult. And also we can expect that the transportation and the reaction rates are significantly increased. And the refractive index distortion and intensive continued radiation from the combustion reaction hinders the quantitative optical measurement method of optical measurement. But still, this is a very interesting problems to solve. So, and we are trying our best to get some very quantitative and accurate information from this combustion behavior. Okay, so we are also collaborating with Professor Sung-Won Kang at Seogang University, and he has done some LES simulation with the same flow conditions we have tested. So as you can see here, it is very interesting. As the pressure exceeds the supercritical condition, the flame oscillation becomes suppressed. So it is quite unexpected, in fact, result we have seen. But in the experiment, we have seen very consistent result. So as the pressure increases and it exceeds the supercritical condition, suddenly the fluctuation of the combustion reaction or fluctuation of the flame front is suppressed significantly. And we have also seen the distribution of Rayleigh criteria, which is a P prime, Q prime, and the normalized P prime and Q prime is presented in the left-hand side here. So at 20 bar, you see a quite fluctuating flow field here, but at above 100 bar, you see a relatively quiet flame field. And we have seen that numbers, and at supercritical conditions, we found that the flame, particularly near the flame root area, is stabilized. So it is good for, considering the combustion instability problem under the high pressure conditions. And we have assembled the 9 injectors like these, and these 9 injectors are combined here to generate really high thermal power. And the size of this combustor is only 9 centimeter by 9 centimeter, but ideally this guy can generate 2.5 megawatts at 101 bar, as we have tested before. So in short, we can say that the rocket engine is proper and desirable for maximizing total power output and you don't need to consider the surroundings. But this guy should carry the oxidizer and more complicated fuel and oxidizer supplier systems, including the turbo pumps. So the size of or the volume of the vehicle will be larger than other air breathing hypersonic systems. So let me continue on the supersonic combustion topics, which is another way of enabling the hypersonic propulsion systems. With the air breathing systems, you don't carry the oxidizer, so the size of the vehicle can be smaller, but stabilizing the flame under the supersonic condition is quite challenging. And also, this guy, this combustion reaction is significantly influenced by the ambient conditions. So the intake air should be well regulated and well compressed, and the turbulence should be well controlled to stabilize the combustion reaction under the challenging high-speed flow conditions. And under this supersonic combustor, scramjet engine means supersonic combustion ramjet engine. So larger portion, at least some portion of the supersonic combustor stays in supersonic regime, so that you can minimize the stagnation pressure loss. Okay, so the flow reaction time now is competing with the chemical reaction time. So you need active flow or flame control methods. So the most straightforward way of doing that is the use of recirculation region behind the fuel jets or captive flame holders. So in the captive flame holders, you have a small recirculation region which produces radical species which can help to stabilize the flame in the free-stream flow. And just behind the fuel jet injection location, you have a wake region where the flame can be easily stabilized. Okay, so this is the OH flip images with the hydrogen fuel here, and these images were taken with ethylene fuel. So you can see very strong combustion reactions is occurring in the wake region and the recirculation region. And in this case, we have added nanosecond plasmas for improving the radical production capability of this recirculation region as well. Okay. So let's see some more details of the flame structures in the supersonic combustor or ramjet combustor. And it looks like this. And we have taken the two-dimensional flame structures using OH flip. And the OH flip has been done by Dr. Chuli Liu. And you can see that the flame structure is quite varying from the center region to the sidewall region. The sidewall is placed at 20 millimeters from the center plane here. So in the boundary layer region, you see a diffuse and a strong combustion reaction is stabilized here. And near the center region, you have a strong shock wave induced diffusion flame just behind the bow shock here, and a strong combustion reaction in the wake region behind. So this is a typical flame structures you can expect in supersonic combustion. And this is the simulation result, and the cells represent the subsonic regime. So if there's empty region, and that's subsonic regime. And with the same flow conditions you have just seen with the OH flip images, the flow will be choked in the supersonic combustor. So the large portion of the combustor will be in subsonic regime, while it is compressed in the supersonic inlets. So due to the excessive combustion reactions generating lots of heat, your flow will be choked and the flow will be in subsonic regime. And under this subsonic regime, the combustion reactions can be easily stabilized. And Professor Vincent Trapon, he is now in University of Liège University in Belgium, has predicted this phenomena before in 2010, and he has been collaborating with me in PSEP program at Stanford University. So here, you can see that the area of subsonic regime expands as the fuel concentration increases. As the fuel concentration increases, one can intuitively expect that the combustion heat release will be increased as well. And then the area of the subsonic regime becomes significant under the high fuel concentration region. So at a 0.5 overall equivalence ratio condition, you can see the over 50% of the cross-section of the combustor will be in subsonic regime. And under this subsonic regime, significant combustion reaction will be stabilized. So you see the change of the flame structure here. And as the flame, as the fuel concentration decreases, you see the flame looks quite different. And at the equivalence ratio below 0.3 or 0.4, we see a scramjet combustion mode, and the flame is long stretched, and probably the combustion efficiency will be lower under these supersonic flow conditions. Okay. So you see two clearly different combustion modes in the supersonic combustor. And this is the simulation result. As before, the cells represent the subsonic regime. So most of the combustor region is in supersonic regime, while the very reactive radical species will be produced behind the jet and the cavity region, which is behind here, which is not shown here. And this radical production will help to stabilize the combustion reaction in supersonic regime. But I would say the combustion efficiency would be significantly lower compared to the LAMP mode operation, where the combustion reaction is occurring in subsonic regime. Okay, so the flow structure in the supersonic combustor looks like this, and Dr. Chuli Liu has presented this in 2014. And as the combustion reaction release the heat in the downstream region, the pressure will be increasing. And due to the downstream pressure increase, maybe through the boundary layer, high pressure region will extend, and it will separate the flow on the side walls and the bottom and top walls as well. So this is the typical flame and flow structures you can expect in supersonic combustor when the flame is stabilized. Okay, so this is the sliced flow structures seen by the Rayleigh scattering measurement method, and you see a bow shock, and the bow shock is generating a compressed flow behind, and the strong weight region will stabilize the flame. And in similar flow conditions, you see the flame is stabilized behind the shocks and inside the sidewall boundary layers. Okay, so these flame structures is strongly dependent on the flow structures, and the flow structure will definitely be produced by the inlets, and the inlet is compressing the incoming airflow, and the incoming airflow could be like Mach 5, 6, or 7, or even higher than 10, and this air speed cannot stabilize the flame inside the combustor, so you should compress it. So depending on the compression ratio at the inlet region, your combustion behavior will be completely different. So as the compression shock wave gets stronger, you can expect a stronger combustion reaction occurring in the combustor. Okay. The scale here is quite different, and for this case, you are taking more air and the shock wave is stronger, so more oxygen, which is compressed more, will be supplied to the combustor, and which is stabilizing a much stronger combustion reaction here. Okay, so that's the reason why people are interested in the design of the inlets. So with the scramjet engines, the inlet is directly connected with your combustor. So not considering the flow generated by the inlets, you cannot control the combustion reaction in the combustor. And there are some different strategies for designing the optimal inlets. So two-dimensional inlets has been designed, which is cheaper and easier way of designing the compression shock waves. And streamline tracing inlet design technology has been also developed so far. And this streamline tracing inlets are compressing the air with higher total pressure recovery ratio. So you can see the quite different result here. So with the two-dimensional and the 2D 3-length compression inlets, the total pressure recovery ratio is only 60% or 50%. But with the same flow conditions, with the very even higher compression ratio, you can expect much higher total pressure ratio recovery. So total pressure recovery is directly increasing your thrust you can get from the scramjet engine. So designing the inlet is a quite important part. And combustion scientists can also design a very nice inlet by considering the combustion behaviors affected by this inlet design. Okay, so inlet design is the starting point of the combustor design here. So we have designed streamlined traced inlets, which is very promising, guarantees the highest stagnation pressure recover, and we have the isolator and the combustor in the downstream. This isolator is placed here to separate the influence of the combustor, which is generating high pressure gas, to the inlet. So without the isolators, compressed and high pressure and high temperature gas can propagate toward inlets to affect the performance of the inlets. So we want to separate the impact of the combustor using the isolator. So this is a nice design which compressed air with very high efficiency, and the nozzle looks like this, which is a parabolic expansion. So what I want to say here is that combustion science can design the entire hypersonic vehicles if you add some background in compressible flow. And with some backgrounds of the compressible flow, you can design a very nice combustor which can be controlled. Starting the control comes from the inlet. Okay, so this is the vehicle we have designed, and we added some more tricks for generating lift force on this vehicle. Okay, so not only the macroscopic flow structures affect the flame behavior in the combustor, the microscopic turbulent characteristics will also affect your combustion behavior in the supersonic combustor. And this is the structure of the arc heaters we have used for ground testing. So high temperature gas will be mixed with the diluent gas by the turbulent exciter. So if you're injecting this gas into the test section without the turbulence damper, then you are expecting highly turbulent free stream air. But with the turbulent damper, you can significantly reduce turbulence intensity in the free stream flow. So this is the Rayleigh scattering images. And without the turbulent damper, you see a very turbulent flow in the free stream. And with the turbulence damper, you see a significantly suppressed turbulence in the free stream flow. With the damped free stream flow, you see relatively weak combustion reaction occurring in the supersonic combustor. But with the same free stream Mach number and the stagnation temperature, you see completely different combustion behavior. So now you have the same compression ratio, same stagnation temperature, static temperature, and the same flow conditions. All other properties are the same, and the fueling rates are the same. But you see a significantly enhanced combustion reaction in the combustor. And we have seen the different flame structures with the OH flip as well. So enhancing the turbulence in the free stream flow will definitely affect your combustion behavior significantly. However, enhancing the combustion is not the best thing you need to consider for designing this hypersonic combustor. As I said, this combustion reaction is interacting with your surroundings. If you have too strong combustion reactions to make too much of heat in the combustor, then you are experiencing the inlet onstrut. So in this case, we have seen the inlet onstrut behaviors with excessive pressure rise in the downstream region. So when you inject too much of fuel, then the heat release could be excessive, and the pressure rise in the combustor could be too much for the inlets. So the high pressure region will propagate toward the upstream, and some kind of very unstable flow structures will be seen. And this fluctuation sometimes spills the intake air, and the air intake oxygen supply will be reduced. And due to the reduced oxygen supply into the combustor, your thrust will be reduced, and then probably the pressure will be decreased, and then your shock will be shallowed again. But as the oxygen supply increases again, then your combustion reaction will be enhanced again, and then it will push the shock wave toward the inlets again. So this is very undesirable situations you want to experience in flight. Okay, so you should stabilize the combustion reaction at designated location. Okay, let's change the topic a little bit. And so far we have used the gaseous fuels for the scramjet combustion. But gaseous fuel has very low energy density. So here the jet fuel like kerosene has like 30 to 50 megajoule per liter. But natural gas or gaseous hydrogen has much lower energy density per volume. Okay, but for enabling the hypersonic flight, you need to minimize the size of the vehicles, so that you need to minimize the drag force in atmospheric flight. Here is an example of the trajectory we have calculated. So you can see here, the dynamic pressure is the most critical limitation of this hypersonic flight. Dynamic pressure is the pressure exerted on your vehicle. If it exceeds like 100 kilopascal, it is very hard to endure this pressure. So you should decelerate the vehicle. So, and we have further optimized this trajectory to maximize flight speed. So flight speed can reach the Mach 10 in this case. And the dynamic pressure is again the most critical limitation here. So you should reduce the volume of the vehicle further for making this hypersonic flight possible. Okay. And we have reduced the altitude and reduced the Mach number here. And the fuel consumption is really significant. It's about 400 kilometers, only for flying 500 kilometers. So the fuel consumption is this much for enabling the hypersonic flight. So in short, for hypersonic flight, you should consume lots of fuel, and the fuel energy density per unit volume becomes quite important. You can maybe choose different trajectories to reduce the fuel consumption, but your maximum Mach number will be below the hypersonic regime. So for enabling the long-range hypersonic cruise flight, liquid fuel should be used. So hydrogens or ethylene are not the option we can have for a long-range hypersonic cruise. But if you're using liquid fuels, there are lots of complications you're expecting. So atomization and evaporations should be considered. Under the low temperature and low pressure conditions, I would say low fuel temperature conditions, as you increase the fuel pressure, you don't see big difference. So atomization and evaporation becomes very difficult. So the fuel injection pressure and temperature and ambient pressure and temperature in fuel types are all very critical for accelerating the atomization and evaporation in the supersonic combustor. In the supersonic combustor, as I said, the reaction time is competing with the flow resonance time. And if you're adding the atomization and the evaporation time, the stabilizing flame will become even more difficult. So you should find a way to heat up this fuel. Okay? And the flash boiling mode, when you heat up the fuel and pressurize the fuel at higher pressure, then you're expecting the flashing mode here, and which is significantly accelerating the atomization and the evaporation. And that helps to stabilize supersonic combustion with the liquid fuel. There are some other alternative, which is the use of gaseous fuel like hydrogen. So hydrogen can be injected with the liquid fuel so that the atomization and the evaporation can be enhanced. But still, you need to carry non-negligible amount of gaseous fuel. So this is not the option for now. Okay. And simulating this supersonic combustion is quite challenging. So because you should consider the evaporation and atomization, and you need some models for accurately predicting that. And it is quite challenging. Although we can see some very similar trends which has been observed in experiments, but still we have to rely on the experiments. So you see different jet structures with jet fuel. Okay, but however, in the experiment, still separately tracking the behavior of the liquid fuel and gaseous fuel is quite difficult. So we have used Exiplex, and Exiplex is the additive into the liquid fuel. So in this case, we are using 5 nanonon, and 5 nanonon has an overlap of its fluorescence with the liquid fuel. The liquid fuel we have used here is the XO-THDCPD. So I know this is a very complicated name, but so this is a very typical jet fuel, and this jet fuel trajectory can be tracked down by exciting this liquid fuel using 355 third harmonic of Perst and the laser. But gaseous jet fuel also emit the same fluorescent. So in liquid fuel, we can suppress the fluorescence by adding this cation. So this is the result. First, you are adding acetone and 5 nanonon, and the fluorescence from the excited liquid fuel looks like this. And below 300 nanometer, almost none of the fluorescence has been observed. But in gaseous fuel, where the 5 nanonon and your jet fuel is separated, still you can excite the jet fuels to emit some fluorescence. Okay. And interesting, the 5 nanonon has quite interesting thermal properties, and boiling point, density, and vapor pressure are quite similar with the extra THDCPD, the jet fuel. So we have added 5% of 5-nano and did some experiments. So for testing the capability of this measurement method, although this is a very qualitative measurement method, we have tested 3 different cases. In case 2, we have heated up the temperature of the free stream flow, and for case 3, we have heated up the fuel and the free stream flow as well. And as you can see here, the liquid signal gets much weaker as the fuel temperature and the free stream flow temperature increases. So that means probably the heating of the fuel will help to evaporate and atomize the liquid fuels in the supersonic combustor. And there are other, in fact, very practical things to consider when you are controlling the combustion reaction in the supersonic combustor. For example, L over D, and L is the length of the injection nozzle, and D is the diameter of the nozzle, in fact, changes the atomization behavior significantly. It is not very clearly seen here, but when you average the field of the fuel fluctuation in the supersonic combustor, L over D changed the behavior of the fluctuation of liquid fuel jets. And this fluctuation definitely affects your combustion behavior in the downstream region. And the diameter of the injection nozzle definitely affects the flow field and the combustion behavior significantly. When you fix your liquid fuel flow rates at 4 grams per second, as you increase the jet diameter, the pressure, fuel pressure will decrease. Okay, so at smaller diameter, definitely you can expect faster atomization and evaporation and the deeper penetration, but it requires higher pumping pressure. That means you should carry heavier and more complicated turbo pump in your vehicle. Okay, that's the issue you need to think about when you are focusing on the evaporation only. And as the fuel temperature increases, definitely the evaporation is accelerated significantly, as you can see here in these 2 different flip images. And also you can think of aerating the fuel jets. So if you place the smaller fuel jets separated by just a few millimeters, then air can get into your fuel jets to accelerate your evaporation and atomization. So this kind of strategies can help stabilizing your combustion reaction in supersonic flow. Okay, and flash boiling definitely is the best strategy you can choose. So when you pressurize and heat up your liquid fuel before it is injected, your atomization and evaporation can be significantly accelerated like this. So definitely you will have to heat up your liquid fuel before injection. But it will consume lots of energy. But you can use the fuels for cooling the combustor, as we have seen for a RAPTOR engine. So your liquid fuel can be circulated around your high temperature combustor, and the temperature will be increased and it will expand a little bit. But when the heating is excessive, it will be evaporated. And inside the fuel supplier lines, you don't want evaporation, because the evaporation will significantly reduce the mass flow rate of your fuel rate. So you want to pressurize it, and you are maybe adding a powerful turbo pump here to pressurize your heated gas. Okay? And heated gas and liquid fuels. Then it will eventually reach the supercritical condition. And under the supercritical high temperature condition, the fuel cracking could be accelerated and gaseous fuel will be generated. And gaseous fuels will be injected into the supersonic combustor, and that will also help to stabilize your combustion reactions. Okay, we'll talk about it a little bit more. And now we know that the benefit of heating the fuel. But if you are using the main combustor for heating the fuel, then it will strongly depend on your flight trajectory and the combustion behaviors depending on the flight Mach number. So one can probably propose the use of subsidiary combustor just to heat up your fuel. So maybe heat exchangers could be placed here for your secondary combustor. And then some of the fuel will be injected into the secondary combustor to heat up the fuel. And if you use some zeolite coated tubes here, then your fuel will be heated up and cracked down faster. Okay, and then supercritical, high temperature and high pressure fuels and partly gasified and cracked down fuels will be injected into the main combustor, and it is quite beneficial for stabilizing combustion reactions under the supersonic flow conditions. Okay, so this kind of supercritical cracking reactions has been investigated very actively recently, and Fan et al. Has proposed the cracking with zeolite catalyst, and with the zeolite catalyst, with the fuel pressure not very high, around 50 bar, and not very high temperature, around 900 Kelvin, the cracking of the liquid fuel can be significantly enhanced, and you are expecting like 50% of the conversion of liquid fuel into the gaseous fuel. So you are carrying the high energy density liquid fuel, and by using these heat exchangers and the catalyst, you can generate gaseous fuel, which can be burnt faster in the primary combustion. Okay, let me summarize the presentation today. So I have mostly focused on the application part of the combustion science. And as you can see, the list of the issues in the fast combustion reactions for hypersonic propulsion, there are many new challenges in supercritical and supersonic combustion applications. And also, we can recognize that there are relevant high-tech technologies, cutting-edge technologies, including the turbopumps and catalysts and materials and vehicle control issues. And all this field should be collaborating to enable the hypersonic flight. And as a combustion scientist, we can maybe focus on the combustion behaviors, but to control the combustion behaviors, we should be using our compressor flow backgrounds to maybe modify the inlets and design the isolators and controlling the microscopic and macroscopic flow structures as well. So, and we also continue on the fundamental combustion investigations and to provide a very accurate first initial gas for making the design constraints and design parameters. We should continue on the very fundamental combustion research as well. So these are some examples and very nice combustion reactions we are fascinated in. Okay. Right. So I hope this presentation triggers some interesting ideas for combustion scientists, and have a nice weekend. Okay. Thank you for your attention.
Thank you very much, Hyungrok. So here I collected a few questions from the audience. So let's go through them. Let me open it up. Okay. The first question, one audience was wondering whether you have any plan to create a prototype of the scramjet, and you design here and test it.
Yes. So I'm working with a national research lab in South Korea. So yeah, we do some real testing, ground testing with the prototypes. But the part I'm participating in designing the prototype is not, I mean, for everything. So I'm mostly focused on the design of the supersonic combustor. So I have designed some stabilization techniques, and yeah, that's it. So we have done, but ground testing under very practical flight conditions. Yeah. So and we have done some tests with the streamline traced inlets as well. So that's another part of research we are focusing on. And we have designed a hypersonic conceptual vehicle with the rest inlets and the combustor, which is diverging with the circular cross-sectional area. And yes, we do some doing interesting research with the research institute in South Korea. Yeah, we have done some practical testing.
Okay. Yeah, thank you very much. The following question is from me. So the supercritical flame you showed is amazing. I like it very much. So I'm wondering, for example, designing such a combustor is very challenging. And how do the combustor wall is cooled, and also for the window, and what is the thickness of the window?
Oh, okay. So we were really scared when we did this test
I'm scared too.
So the pressure was really high. So the maximum pressure we have tested was 200 something bar. So to endure that high pressure, we need multi-layers for cooling, like you said. So most inner layer looks like this. The thickness, this really over-designed, but anyway, first design was like circular windows, but the circular windows blocking too much of the optical axis. So we changed the design to the rectangular design. And with the rectangular design, you need a thicker optical axis window. So with the circular, we could like design like 3 centimeters in the inner layer, but with the rectangular design, we should make it like 7 centimeter thickness. So this is really thick
that is
inside. And this combustor is now installed in a high pressure chamber. So this you can see is for fitting into a larger high pressure chamber. And in the larger high pressure chamber, you're pressurizing it with like 70 bar or 80 bar, so that the inner layer can endure lower relative pressure difference. So the inner layer endures roughly 70 or 80 bars pressure difference. And the outer chamber has another thick optical axis window to see inside. That was about 50 centimeter thick. It is, I would say, it's a really over-designed because we were scared.
Right. Oh, that's really interesting. Thank you very much.
And the cooling with the CO2 has been done between the 2 layers. So we are injecting large amount of CO2 between the 2 layers. Okay.
So next question. So first, the audience want to thank you for this great presentation. And he noticed that a circular scramjet combustor was used. So he was wondering, why do you choose the circular combustor instead of a rectangular one? And how do you solve the problem of refractive index distortion in your optical measurement when using the circular combustor?
Circular combustor. In the circular combustor testing, we don't have optical axis here. So what we measured is only the pressure. So it is a really good question, and it is very challenging, and we don't have plan to make an optical axis for the circular combustor. So the one most critical thing here is that it will depend on the trajectory you are designing. So our trajectory I have designed is very challenging trajectory. It is starting from Mach 3.5 because we want to reduce the size of the boosters, which provides the initial acceleration. So from Mach 3 to Mach 8, you should take the air with various different conditions. And with the various different conditions, your combustion control strategies becoming very complicated. So, for example, let me show you very typical strategies for fuel injections. You have multiple layers of fuel injections for stabilizing flame under those variable flow conditions. And under a special, the very typical range of Mach numbers, you see a very serious high pressure flow propagation from the combustor into the inlet regions, and these are through the corner flow. So through the corner flow, you don't have a high pressure region. You have the high pressure region, and that high pressure region make a secondary flow, and this secondary flow enhances the propagation of the high pressure region toward inlets, and that is making a big problem in the inlet compression. So we want to avoid this problem, and minimizing the secondary flow generation, the choice was the use of circular cross-section in the combustor. So that's why we have used the circular combustor, and making it is easier. And structure, if you have a rectangular design, the structure consideration becomes much more complicated. I'm not a structure guy, but structure part, I mean, the researchers in structure part told us that making a circular design make them much happier. So we just tried the circular one. But I'm not sure if the circular is superior for all the fields, but at least for the structure and the secondary flow generation, circular is superior. So that's why we tested.
I see. Thank you. So the following two questions from Isaac. So the first question is whether we need to worry about the coking of fuel lines when preheating the fuel.
Yeah, coking is a very difficult question, I mean, to solve. So if you're using a typical stainless steel supplier tube, it will start to be degraded, and the heat transfer through the fuel tube will get reduced significantly within like 10 minutes or 15 minutes. So for the first test flight, I mean, this is not designed for the first test flight, but anyway, if you are flying less than 10 minutes, mostly the coking is not a big problem. So it takes some time for developing of the coking on the surfaces. But if you are designing a long-range hypersonic flight over maybe 20 minutes, then you should be seriously consider the coking problem. But for now, we haven't considered that very seriously, but we have seen some coking problem as well. So we should change the heat exchanger almost every time after the testing if you're using just stainless steel supply line. So the heat transfer rate is significantly reduced for the heat exchanger. Yeah.
The second question, were the turbulence generator grids you used in the scramjet combustor experiments active or passive type?
Didn't get it. Could you tell me again one more time?
Yeah. So for the turbulence generator, right? So it's a mesh, and are those mesh active or passive type?
Oh, these are passive type. So we can change the shape of the turbulent exciter, but in this case we have used a fixed geometry. So probably if you want a different turbulent characteristics, definitely you can change the shape of the turbulent exciters, but we haven't tried many different cases. So we just focused on the fast mixing of the heated gas and the diluent gas before it's getting into the CD nozzle. So yeah, unfortunately, we couldn't actively control the turbulence excitation.
Yeah, the last question on my list. So for quantitative diagnostics being challenging because of the supercritical conditions and the index of refraction. So the question is, what optical diagnostic techniques have been successfully implemented in the supercritical region?
Okay, so that's a really good question. So that's what exactly we are now thinking of. So refractive index distortion is too serious here, and maybe we will not be able to see the two-dimensional planar distribution of something. The planar beam will be distorted significantly. We have optical access window here, but we tried that, but it was seriously distorted. So even in the subcritical conditions here, you see the significant heat release from the combustion reaction distorted refractive index field. So, and we are injected a straight tunable diode laser into the combustor, and it is distorted significantly, and it is fluctuating too much. So far, only one thing we could measure was the emission spectrum from the supercritical combustion reaction. But as you can see here, maybe from water and CO2, the significant continuous emission masses of everything. So seeing some emission lines and bands are almost impossible for now. So we are just trying other techniques, but for now we have very limited capability of seeing quantitative laser diagnostics tools. Yeah.
I see. Is the fuel methane here? Okay. Yeah. I'm curious. For example, if you take a picture, a direct photograph of this supercritical flame, So that means we could not even trust the image because it's distorted.
Yeah, even the pictures, I mean, you are taking. Yeah,
for example, if I want to look at a flame structure, so probably I should not even trust the direct photograph.
Yeah, right. So that's why we started LES measurement. So the flame base should be somewhere here, but as you can see here, as the pressure further increases, the distortion becomes much more significant, and even you cannot see this. I mean, igniter here. So,
I see. Yeah,
seeing the flame structure is almost impossible. So with the LES measurement, which is considering the supercritical properties as well, but maybe it will looks like this, but the flame is quite diffuse. That's what I think why it's hard to see the flame structure clearly. And the bluish fluorescence from methane cannot be seen here because of the too strong continuum emission. So I mean, it's a big problem for now we have to show. So and I need some comments or help from the combustion scientists here.
Okay. Yeah, thank you very much.
Thank you.
Yeah, that's all the questions I received.
Okay.
So probably we could turn on the camera if you could, and thank Hyungrok, a nice presentation for today.